Okay, so today I'm hoping to get pretty much through the rest. Well, I don't know. Um, yeah, I'm thinking I'd like to get. Well, let's see. How many questions do we have here? Well, 7, and then many parts. Um, yeah, I think. Um, yeah. Anyway, so I'm gonna be working for like a couple hours today on this. Yeah, a couple hours. Um, and so hopefully I will be able to get through the most of the portion. Actually, I think I'm gonna probably work for like um, yeah, 2.5 hours. I'd like to finish up pretty much all of the exam, such that we'd been in a reasonable spot for me to hop onto this next. Oh, let's see. Oh, this is part B. This one here. Hop onto this next exam here, part B. Um, yeah. I think if we go through each of these, I will have to. I am going to look over and see if there's anything that um, I don't know from this one that exists in that one, and we'll study that before. So it's not like a pure environment exam, but I do want to be able to complete each of the things. Okay. Sweet. Yeah, I think we'll just go ahead and start. So, oh, actually, we'll have to do Anki. Okay, for rational functions, you find horizontal asymptotes. First, you look at the denominator and the numerator. And if the denominator has or the leading coefficient of the denominator is 1 larger than the numerator, or I guess 1 larger, or even more than that. So I guess if the denominator's highest leading coefficient is more than the numerator, or if they're equal, or sorry, if it's more, then you know that the asymptote is 0, and if they're equal, then the asymptote is the ratio between the highest numerator, or the leading coefficient, or yeah, is the ratio between the leading coefficient for the numerator and the denominator. Okay. Yep. Compare. Yep. Is less than asymptote is 0. Yep. If the numerators, or if it's equal. Yeah. Okay. Perfect. That's exactly it. So I still need to do. Okay. So L'Hopital's rule. I believe when we're doing it, we will. If I'm recalling correctly, this is where we take the. I feel like you take the derivative of it and see if you can find the limit then, but that doesn't seem correct. Or perhaps this is where we're this is the rationalizing of a function. Let's see. Differentiate the numerator and denominator separately. Take the limit of the new fraction. Okay. A limit for rational functions. Okay. Okay, so I do need to. Interesting. Okay. So we're gonna. So I first need to confirm that, and then differentiate the numerator and the denominator separately. But that one, a slanted asymptote. So this is when the The numerator is leading coefficient is 1 higher than the denominator, I believe. And you take the, well, I don't know if that's the case. I know we're dividing the numerator and the denominator using polynomial long division, but I can't recall beyond that. No, it's exactly 1 higher. They performed polynomial long division. The quotient is the slant asymptote. Okay. We'll send that one back through. Horizontal asymptotes for non-rational functions. You look where non-rational functions. I guess you take the limit as it approaches infinity and see if it converges on a finite number. Okay. Okay, so you want to take the limit and see if it's undefined. Or sorry, directly take the limit. If we come back with a finite value, then we have one. If we don't come back with a finite value, analyze the limit from left and right side and see if they're equal. Additionally, you can also... additionally, you can also try to grab an algebraically equivalent function. So if it's a complex function, actually not complex in the mathematically precise sense, but if it's a function that has a lot of stuff going on, you can try to find an algebraically equivalent function. Let's see. Yep. Okay, so yeah, okay, I think this is reasonable. So I had this part. The reason why I added the algebraic equivalency for a function is that because sometimes the limit doesn't exist initially, but it exists after you factor it out. Okay, I'm actually going to spend a little time here because I believe we have something I don't understand. I'm learning about calculus, period. Could you tell me the process to go through to find if a function has a limit? Okay, so I'm thinking that there's a little bit more. So for this one here, evaluating the limit from the left and right, I'm thinking that this should only be done if the complex or the function isn't so we perform L'Hopital's rule on a function, right? And the reason for that is to simplify it. So there's also approaches where if it's doesn't seem ready to be taking if we take the limit from the left and the right, then we ought to do something more there. Okay. Okay. So this is what I was talking about earlier. Indeterminate forms. Okay, so we're doing L'Hopital's rule. If the limit is indeterminate. Okay, so L'Hopital is used to evaluate indeterminate forms. Okay. So I think I'm going to add a card there. I just want to check to see how... Okay. Okay. Expression is something that doesn't have a like equal sign, or doesn't take inputs and go to outputs, like one or more terms. Okay, I also want to add to this, if the form of the function is indeterminate, you can also evaluate you can factor okay. Okay, I feel pretty good about that. Let's see, I'm going to read through this entire thing to make sure that we got everything. I'm going to zoom in as well. Okay, I got to remember to zoom in each time, lols. Okay, determine if a function f of x has a limit as x approaches a point C, follow the steps, understand the limit concept, blah, blah. Evaluate the left-hand limit. If it gets close to C from values less than C, substitute values slightly less than C and simplify the function. Evaluate the right-hand limit, see what happens when we approach C from the other side, from greater than C. Compare the limits if positive and negative C both are finite numbers L, then the limit exists at L. If the left and right limits are not equal or one does not exist, the limit does not exist. Okay. The function is continuous at x equals C. Try substituting x into C, or sorry, x equals C into f of x. If f of C is defined as finite, the limit is f of C. So if I have a value C that I substitute into my function f of x, and it returns a finite value, do I need to check the left and right limits to determine if those exist and they equal each other? Or is it okay to merely just conclude that the limit is C. What C evaluate is the finite number C evaluates to. The finite number C evaluates to. I'm pretty sure it's okay to go for just C. That's my tuition. Okay, perfect. So that is correct. Okay, compare the limits. Yep. Check for direct substitution. Handle intermediate forms. Okay, I think I do want to grab a card of what an intermediate form is, and that can go through there. L'Hopital's rule. So this is where we take the derivative of, or sorry, we differentiate the numerator and the denominator. And then we take, and then we do that and then see if we can take the limit at that point. Okay, we got to confirm first that it's indeterminate. What does it mean for a function to be in indeterminate form for calculus? And I assume that this indeterminate form is only in regards to calculating a limit. Okay, so I'm going to do AKA in indeterminate form. So a good rule of thumb for using L'Hopital's rule is to check if the function is in an indeterminate form. Are there other situations where we'd want to use L'Hopital's rule? Okay. Okay, so primary situations is we're looking at when we have an indeterminate form. Okay, it's designed for that. There's no common situations where you use it without an indeterminate form. Okay. So we can also just keep repeating it as well, which is kind of nuts. Okay. Okay. Perfect. So, oh. Okay, so I feel good about that one now. If the numerator is 1 degree higher for the polynomial's leading coefficient, then you take the ratio of leading coefficients, or sorry, yeah, you take the ratio of leading coefficients, and that's the result. Is exactly 1 higher. So if the degree of the numerator, let me check this, because this isn't the same language I was using, and so I want to make sure that's the same. Could you give an example of this with binomials in the numerator and the denominator, and then also polynomials as well, where we have 3 terms each? Okay, yep, same term. Maybe I just need to know how to calculate degrees here. Identify with the highest exponent. The degree is the value of the highest exponent. Okay. Yep. Okay, that's correct. Okay. So derivatives relate to the slope, and integrals relate to the area, because integrals are area under the curve. And calculates if the results of taking the left and right hand limits result in positive and negative infinity for a given function. Does the limit of the function exist? It does not exist. They need to be equal to be. They need to be equal when taken from the left and the right. Lagrange is the apostrophe syntax, and the Leibniz is the syntax that emphasizes the rate of change, I believe. And it uses square brackets. Lagrange notation. Okay. As a ratio. Okay, does not use square brackets. We're going to send that one through. So it's d over d. I don't know if this is correct. This seems like, I don't know. This seems not correct. Oh, okay. So I'm just going to actually take this. Oh, it did not work. We'll just add that a little bit. Okay. So we're gonna swoop. Okay, so when value C is not directly substitutable, we can find an algebraic equivalent of the function to see if that one returns a limit. In indeterminate. Okay, indeterminate forms or undefined expressions. Okay, I'm actually going to make a card that is the distinction between those. So undefined is when we're over 0, I believe. Indeterminate is when we're 0 over 0 or infinity over infinity. And this may seem like a weird thing to compare, because to isolate, I just gotta disconnect it, reconnect it. Okay, I think we're good. Okay, that was odd. Okay, anyway, so they exist within a similar conceptual space in my mind presently, and so it's good to ensure that I have a distinction between them, and then also creating this distinction will really yeah, really make it clear in my mind. Okay. Okay. Perfect. Do I have any more? Okay. Yep. Okay. See if C or the value C exists given the limit of like taking the limit of C. If it doesn't, we can use some algebraic equivalency to figure, or we can use some algebra to see if we can factor out necessary things such that the limit does exist. If that still doesn't help, then we take the limit from the left and the right, and if that exists, then that exists. If those exist, then they equal each other. That's the limit. Additionally, if we have an indeterminate form, we can use L'Hopital's rule, or we can factor, rationalize. As when we're dealing with an indeterminate form, we take the derivative, the upper and lower ones, and we try to take the limit of it again. Okay, perfect. Undefined expression is one where like 1 over 0. Indeterminate forms, or sorry, undefined expression is 1 over 0. They don't have like real value in terms of like, you know, what value is described as. And indeterminate forms are where you have like 0 over 0 or infinity over infinity that require further investigation. We use L'Hopital's rule, Lagrange notation, and Leibniz notation. Leibniz notation focuses on rate of change and is like d over dx. And Lagrange notation is the prime notation. Okay. Perfect. Okay. So we got through those. We did pick away some lack of understanding. So that was good. I am going to probably need some time on the trigonometric functions. But where are we at? Find the limit of exists. So we're at 3, 4. Okay, yeah. So I think I need to spend some time on the trigonometric functions. And I feel like I actually did spend some time. Oh, maybe I closed that one out. But we do have this. Perfect. Okay. So let's see. Should I spend more time on that? I think I would like some yeah, because this right here is lacking. But like really diving into this would require I probably hold off on what I'm presently doing. So maybe no, I think it's reasonable to like focus on this presently. We're just going to be pretty much creating a lot of cards. Yeah, I think it's fine to focus on this right now. Okay, calculus, because we'll need to do it eventually, and so unless I see some benefit of having the overview take place in a more less like, I don't know, disjuncted manner, then I like should just opt for doing it right now. And yeah, okay, perfect. Could could you describe the understanding needed for the various trigonometric has trigo functions in order to get by in a Calculus 1 class. Okay. Okay, so I know okay, graphs of trigonometric functions, understand shapes, periods, and key features of trigonometric functions. Function graphs, they help with limits, derivatives, and analyzing behavior. Okay. Trigonometric functions and limits. They often involve indeterminate forms requiring specific identities or techniques. This is more than I was anticipating. I don't know if I have anything in regards to the unit circle. Okay, so let me pull back. I think we'll focus on exactly what's required for the test. And so it seems that though it is described that all this is needed, I should be able to get by with, only that which is needed, right? And so I guess this is kind of a bit. Okay, so let's see. I think if I would memorize the identities, which I pretty much mostly have, so we'll just put a couple of these into Anki cards. I don't think I'll need to have these common angles down. I don't believe that we have many instances where that's the case. Okay. Okay, so I think we'll first go over some of these. I'm gonna refill my soda first, though. Okay. Okay. What should I have? I think understanding these would be good. I think understanding the Pythagorean identities would be good. Let's see what things are on here. Cosine, I only seen one cosine here. Yeah, I think the okay, I think we'll just keep going through. I think one thing that I'm recognizing is I spent a lot of time on the conceptual side, so I'd be able to talk through something like a lot of these topics with someone, but because of the I don't have much like procedural prowess yet. Yeah, I think that's what presently I'm thinking. Okay, so okay, I think I'll just grab a couple of these. Okay, so I'm probably just going to look for okay, this is oh, okay, so here's the chain rule, so that's important to know. Okay, maybe I'll write down what I'm needing. Oh, actually, okay, so I think these can be evaluated via the process of using like the power rule. So I'm not super worried about that. So I'm going to need the chain rule and reverse chain rule. And then I'd like to have the Pythagorean identity. This main one, because I feel like I'll be able to derive these other ones having the main one. So we'll just do like main one, double angle formulas. Maybe a double angle formula. reciprocal and quotient identity. And then core trigonometric functions and their definitions. Okay, I feel like having those things, I will be able to get everything I would need to for this. I think the big thing that I'm missing right now is, yeah, that procedural aspect. Because even though if I have these things, being able to identify when they need to be implemented is another thing. So I can hope that it'll be the case that I'll be able to identify it, but it's not clear that it will actually be, I'll actually be able to like reliably get that, you know, or it might take a bit, which if I'm giving myself a time constraint here, wouldn't be great. Okay, so I think I'm going to grab okay, I think I'm also going to grab the ranges for the trigonometric functions. Okay. And maybe I'll say which of the following functions have an unbounded range, right? And which ones are bounded, which ones are unbound or have unbounded range outside of -1 to 1. And I think that should probably be sufficient for that one. Okay, so given those things, I think I will have enough like trigonometric literacy that I'll be able to squeak by. Okay, yeah, so let's grab all these and then we'll just kind of keep chugging along. So I'm gonna open up a new chat so I can reference the previous one. Okay, could you describe the chain rule in calculus? Okay, so it sounds like previously. Oh, okay. So I was looking at the definition just briefly, and I think it represents when we have a composite function where one function takes in. No. Well, so I'll just say what it is, what I think my hypothesis is from my brief looking at it, and then we'll correct myself. So I think that it is the property that allows you to separate out functions. No. So this, okay. The separate out function. So for a composite function, f of g of x, it would allow you to do f of x and then something and then g of x. But like it doesn't make sense to have those functions associate via like a addition or anything like that. So so that's what I saw. I'm not 100% sure because that's clearly not it. But let's read it. Okay. A chain rule is used to differentiate composite functions. So it deals with composite functions, but it's different. Okay, if you have a function f of g of x where f is applied to the output of g, the chain rule states that the derivative is f of g of x, this guy, multiply. Interesting. Wow. That's weird. Okay. Whack. Interesting. Okay. So I'm going to pull up my card now and see if I get it. Okay. So the reverse chain rule is a technique that it's a technique in integrate. Oh, sorry. Chain rule is a technique in integration. It's used to differentiate composite functions. If y equals f of g of x, then the derivative is dy over dx equals f prime gx of, or f prime g of x multiplied by g prime of x. It expresses how change in x affects y through an intermediate function. Okay, I think that's reasonable. So if it is the case that this is the chain rule, then how would that relate to an integration? So since I know integration is an opposing function, it could be the case that the function's relative positions are switched. That seems unlikely because it's probably a different operation, but let's give it a look-see. Oh, okay, no, that's correct. No, wait. Wait, what? The reverse chain rule in integration, also called U substitution, is where you identify an inner function and its derivative, allowing you to integrate a composite function by reversing the change rule from differentiation. It's used to simplify and evaluate integrals of the form. Okay. So let's see now. Could you now tell me about the reverse chain rule? Of finding antiderivatives by reversing the logic of the chain rule for differentiation. It applies when an integral involves a composite function, allowing you to transform the integral into a simpler form by substituting a new variable. Perfect. The chain rule for differentiation states that f of g of x, or if y equals f of g of x, then dy over dx equals f prime g of x times g prime of x. When integrating, the reverse chain rule helps us recognize the integral form. F of g of x times g prime of x dx, which is the antiderivative of a composite function. By substituting u equals g of x, the integral simplifies to f prime of u du equals f of u plus c equals f of g of x plus c. I'm not sure why we're using u. It seems like it's just a random variable, so maybe it's just typical that u is used in this operation. Okay, let's go through the implementation and see if this makes sense. Identify the composite function, look for an integral where the integral integrand represents f prime gx multiplied by g prime x. Typically, the part of this integrand is the derivative of an inner function gx. Choose a substitution. Set u equal to gx, where gx is the inner function. Compute the derivative du over dx equals g prime of x. So du equals g prime dx. Rewrite the integral. Express the integral in terms of u, replacing g prime x dx with du, and with and f prime gx with f prime u. Could you describe the reasoning for picking u? It seems like it's just an arbitrary thing that it... Could you describe the rationale for picking u? Question mark. Is this merely the variable that is used for this operation? Question mark. Could you describe how it is the case that this substitution simplifies things? I'm still not clear about the mechanics of it. Additionally, could you describe what substitutions occur when we do this operation and be explicit about each one? Okay. The inner function of a composite function within an integrand. Okay. I think integrand is a function to be integrated, or is it a integrated function? Damn, nice. A function that is to be integrated. I think I'll add that as well. Okay. The variable, okay, so we're going to integrate this thing, match the chain rule structure. The integrand often resembles the derivative of a composite function, i.e. it resembles f prime gx multiplied by g prime x as produced by the chain rule by setting u equal g of x. The inner function g of x is isolated, and its derivative g prime of x, or a constant multiple, should appear in the integrand to allow substitution of du equals d prime of x dx. Simplify the integrand by the substitution u equals g prime, g of x aims to collapse the composite function into a single variable u, making the integral look like a standard form. Ensure du is present. Derivative du over dx equals g prime of x must be present or differ by a constant in the integrand so that du equals g prime dx can replace part of the expression. How to pick u? Look for a composite function, identify a function gx inside another function, x2 in sine of x, or x3 in e to the x to the 3. Ensure that g prime or a constant multiple appears in the integrand, for example, in integration of the 2x cosine x squared dx. 2x is the derivative of x squared. Okay. Multiple choices seem possible. Try the one that simplifies the most. A good u often makes the entire integrand expressible in terms of u. Frequently, the u is chosen as the exponent in an exponential. the argument of a trigonometric function, the expression under a power or a root. The integrand has 2x squared plus 1 to the 3, suggesting x squared plus 1 as the inner function. The term 2x is the derivative of x squared plus 1. Yeah, that makes sense. Choosing u equals 2x, or sorry, x squared plus 1 is logical because du equals 2x dx, which matches 2x dx in the integrand, simplifying the expression to u3 du. If the derivative u to the 3 du. If the derivative doesn't match exactly, you may need to adjust with constants or reconsider this substitution, as the factor x is not a perfect match for dx. Okay, so for the example rationale section where you have x squared plus 1, it does make sense that if we differentiate the inner function, which in this case is x squared plus 1, we get 2x. However, I'm not sure why this would be done. It does, yeah. Could you describe the use of taking the derivative when we were looking for the antiderivative? Okay, so when the goal is to find the antiderivative using integration by substitution, this is a great question as it touches on the core logic of why integration by substitution works and how differentiation plays a role in the process. Let me clarify the rationale and mechanics behind this step, specifically in the context of the example. 2x x squared plus 1 to the 3 dx. Explain why differentiating inner functions is essential even when seeking an antiderivative. When performing integration by substitution, the goal is to simplify an integral such that it resembles the form of composite functions derivative, a composite functions derivative, okay, as produced by the chain rule. The chain rule for differentiation tells us that if y equals f of x, or f of g of x, then dy over dx equals f prime gx multiplied by g prime of x, or g of x. For example, if y equals x squared plus 1 to the 3, the chain rule gives the inner function of x plus 1, so g prime equals 2x. The outer function, f prime Okay, so the chain rule is about like equivalency here, right? And so it's reasonable that we can pull it out into this different form. Notice this integrand 2x, oh, okay, looks similar to this derivative, except the constant 3 is missing. Similarity is key. Integration by substitution works when the integrand includes or is closest to the derivative of a composite function, because the antiderivative reverses the chain rule. When we choose u equals gx equals x plus 1, we need to compute du over dx equals g prime of x 2x equals 2x, which gives us du equals 2x dx. Step is crucial because it matches the integrand. The term 2x dx in the integrand corresponds to du. This allows us to replace 2x with du, simplifying the integral. Facilitates variable change. The substitution u equals x squared plus 1 changes the variable of the integration from x to u. To express the integral in terms of u, we need du, which comes from differentiating u equals x squared plus 1. Reverses the chain rule. The presence of g prime of x equals 2x in the integrand signals that the integral is the result of the chain rule via differentiation. By substituting u equals gx, we undo the chain rule, transforming the integral back into a simpler form involving f of u. In short, we differentiate the inner function to find du equals 2x dx, because this differential allows us to rewrite the integral in terms of u, eliminating the composite structure and making the antiderivative easier to compute. It helps us to find an antiderivative. The process of integration by substitution is about recognizing that the integral is structured like the derivative of a composite function. By choosing u equals 2x plus 1, we aim to reverse the differentiation process that would produce 2x x squared plus 1 to the 3. Here's how it connects. Pattern recognition. The integrand 2x, has two parts, one of which is this gx, 2x, which is the derivative of the inner function. Okay, so I think the one thing that I'm not getting is that, like, how is it the case that, so I understand that when we're using the reverse chain rule, it is when we have a function of a function, and then so that, like, right here, so I understand that it's the case that when we've used the chain rule to get our, so the chain rule for a composite function, it results in this form, f prime gx times g prime of x, and this is the antiderivative using, or this is the resulting antiderivative that we found through use of the chain rule. Okay, so let me just double check that. I'm actually gonna do another one. Lols. Is the goal of the chain rule to be able to differentiate Okay. Okay, perfect. So the goal of the chain rule is to be able to differentiate a composite function. Okay. So if the goal of the chain rule is to differentiate a composite function, and given that differentiation and integration are opposing inverse functions. So given those two things, then it should be the case that if we have a form that allows us to take, or that allows us to take a function to a derivative via the power rule, I guess this is the chain rule, then we would have an inverse function that takes us from the resulting form of the derivative as a result of the reverse chain rule to our integral because of the inverse nature of these functions. No. It's not because of the inverse nature of these functions. It's because that, well, yes, it is actually in part because of the inverse nature of these functions, but it's because it's because the power rule, I'd say it's because the power rule works for, not the power rule, the chain rule works for differentiating a complex function. We know that there is a reverse chain rule that exists that takes us from the resulting form of the chain rule and brings us back to a state similar to the base level composite form for a function, which would be its integral or antiderivative, I believe. Okay, so being that that's the case, I think the U substitution portion is probably I think there is some issue with I think there is some issue with, so I guess when we apply the reverse chain rule, it's through our ability to recognize the form of the function as the same form of the it's the same form as the result of a composite function that has undergone the chain rule. Okay, I feel good about that. And I think the U substitution, or using the U to substitute things, I think it's like a guide, or like it sort of helps you along the path. I think you could probably do it without. I'm going to see if my explanation is correct. Okay, so I think I'm actually, we're going to go to this one. This one. Okay, so I think I'm sort of following now, period. So I'll first describe the chain rule and the reverse chain rule, and then I do have some questions about U substitution, or I guess the application of the reverse chain rule and why we're going about using U for the substitution process, period. Okay, so the chain rule allows us to take the derivative of a composite function, and it allows us to do this in terms of a form that emerges as a result of this function, period. It is the case that for a function f of g of x, the resulting form that's generated through using the chain rule is f prime of g of x multiplied by g prime of x, period. It is the case then, because of this relationship between a composite function and its resulting derivative form using the chain rule, that there is a similar rule, in this case, the reverse chain rule, that can be used for integrating a particular form of a function, period. This form represents what appears to be the result, in form, not in actuality, of the chain rule. if we are to use the reverse chain rule, it is because it matches this relationship or form. Period. The form is this. We have a inner function that matches a term. No. The form is this. We have an inner function that, if we took the derivative of, would match a term that is being multiplied on the result of the outer function. Period. When this is the case, we can choose the when this is the case, we can use the reverse chain rule to take us from this form to an integral or an antiderivative. Period. Is this the case? Question mark. Okay. So if this is the case, or I guess regardless if this is the case, could you now describe what we set u to? Is it the inner function, or is it the derivative of the inner function, which would be the outside term that's multiplied? Okay, we'll see how that goes. Okay, I'm correct that the chain rule is used to differentiate composite functions for a function f of g of x, where f is the outer function and g of x is the inner function. The chain rule states that the derivative of this is f prime of g of x times g prime of x. F prime of g of x, the derivative of the outer function evaluated at the inner function, g of x. G prime of x, the derivative of the inner function with respect to x. For example, if y equals sine of x squared, let f of u equals sine of u, and g of x equals x squared. Then f prime of u equals cosine of u, so that f prime of g of x equals cosine of cosine of x squared. Okay, and I think this the sign has become cosine because of the power rule. Maybe. So the resulting derivative would be the cosine of x squared times 2x. You're also correct that the reverse chain rule or integration by substitution is used when the integral resembles the form of a chain rule derivative, i.e. f prime of g of x times g prime of x. The goal is to find the antiderivative, effectively reversing the differentiation process. If the integrand looks like this, f prime of g of x multiplied by g prime of x dx, we can simplify it by substituting u equals g of x, which transforms the integral into this. F prime of u du equals f of u plus c equals f of g of x plus c. Key insight: the integrand must include g of g prime of x, or a constant multiple of it multiplied by a function of g of x. This matches the chain rule pattern allowing, let's see, the integrand must include g prime of x or a constant multiple of it multiplied by a function of g of x. Okay. This matches the chain rule pattern, allowing substitution to simply simplify the integral. For example, for 2x multiplied by cosine of x squared dx, the integrand 2x multiplied by the cosine of x squared resembles f prime of g of x multiplied by g prime of x. Yep, okay, understand that. Okay. So it matches the form. So we use the reverse chain rule when the integrand includes a term that is the derivative of an inner function multiplied by the function of the multiplied by a function of the inner function. This allows us to substitute and simplify, finding the antiderivative. Okay. Okay, so I think given that we're in this situation with f prime of g of x, what we only need to do is we need to use the power rule to integrate the f prime, and then we can merely keep the resulting g of x and drop the last term. Clarification, you mentioned the form represents what appears to be the result in form, not in actuality, of the chain rule. This is a good way to describe it. The integrand doesn't need to be the exact derivative of a function, but it should structurally resemble it. For example, resembles the derivative of x squared plus, adjusted for constants, which why the substitution works. Now let's address your specific question. In the integration by substitution, what do we set u to the inner function or the derivative of the inner function in turn, or the term being multiplied? We set u to the inner function, not its derivative. The derivative of g prime of x is used to compute the differential du equals g prime of x dx, which facilitates the substitution. Why the inner function? The inner function g of x is the part of the composite function that, when substituted as u, simplifies the integrand. By setting u equals g of x, we replace g of x with u, turning expressions like f prime gx into f prime of u. The derivative g prime of x appears in the integrand as a multiplicative term. Its role is to provide du, allowing us to replace g prime of x dx with du. Setting u equals g prime of x, the derivative, would typically complicate the integral, as g prime of x is not the argument of the outer function. Okay, so consider 2x multiplied by x squared plus 1 to the 3 dx. Inner function, suggesting it's a composite function. The derivative of the inner function, g prime of x equals 2x, so du equals 2x dx. Setting u, will you choose u to equal 2x plus 1, that's fine. Not the derivative of it. If 2x, or if u equals 2x or x squared plus 1, then integral becomes just simple. If we mistakenly set, that's fine. Thus, u is the inner function and provides the differential du. It's the use of u as a substitution variable is a convention to change variables. The integral is originally in terms of x. By setting u equals g of x, we rewrite the integral in terms of u, simplifying the expression. Simplify the composite function. Composite functions like x squared plus 1 to the 3 cosine x squared are hard to integrate directly. Setting u equals x squared, but it collapses these into u to the third cosine u or eu. Leverage the chain rule pattern. The substitution works because the integrand, standardize the integral. The resulting integral is a standard form we know with a known antiderivative. The letter u is just a convention, but it represents the new variable that replaces the inner function. Okay, we already know that the u is the inside function. Okay. Okay, so... Okay, so I'm now thinking I'm grasping it a little bit more. So let me describe something to see if this is the correct way to think about it, such that... Oh, yeah. So, if we are wanting to find the integration that is the result of using the reverse chain rule, we first must identify if the function matches the form of the result of using the chain rule. Period. This form is f prime of gx multiplied by g... Ah, shit. Okay, this form is f prime of gx multiplied by g of x. Oh, it's g prime. This form is f prime of gx multiplied by g prime of x, period. Given what we know about the chain rule, the reverse chain rule will take us to the original composite form, which is f of g of x, period. Meaning, if we see the function we are wanting to integrate in the form of the result of the chain rule, then we can merely drop the term that is multiplied by the outer function, and we take the power rule of the outer function to find its integration, and then we keep the inner term the same because of the relationship between the inner function when we use the power rule. The chain rule. Okay, we'll see how that rolls. Description shows that you're getting a solid grasp of the reverse chain rule, how it relates. You're correct in identifying that the integrand must resemble the form yep, and the reverse aims to recover the original composite function. However, there are a few points ensuring actually, particularly around dropping the term and applying the power rule. I'll refine your understanding, confirm what's correct, and address potential misconceptions, including your description as a guide. Then I'll summarize the process to clearly solidify your intuition. Analyzing the description, let's break down your explanation and identify the form. You said, we must first identify the function that matches the form. Yep, correct, okay. You said, the reverse chain rule will take us to the original composite function, which is f of g of x. Okay. You said if we see the function in the form of the result of the chain rule, then we can merely drop the term that is multiplied by the outer function and take the power rule of the outer function and find its integration, and then we keep the inner function term the same. Partially correct, but needs clarification. Drop the term that is multiplied. This is likely refers to the g prime of x. Yep. We don't exactly drop it. We replace it with du, where u equals gx. Oh, so d is the derivative. Oh, okay. This step accounts for the derivative term, allowing us to rewrite the integral in terms of u. Take the power rule of the outer function. This is correct in cases where the outer function's derivative is a power function. Oh, okay, so it's not a... Okay, so power rules are only in power functions. That's obvious. Okay. This is correct in cases where the outer function's derivative is a power function, but is not universal. For other functions, you integrate f prime of u according to its antiderivative, not necessarily the power rule. Keep the inner term the same. This is correct in the sense that the inner function g becomes u. After integrating, we substitute u equals g of x back, preserving the inner function in the final antiderivative. Integration is heading in the right direction, but instead of dropping the term and assuming the power rule could lead to confusion in cases where the outer function is a power function, or when constraints are involved. Constants are involved. Let's clarify with examples and a precise process. The reverse chain rule integration by substitution works because it reverses the chain rule's effect. Here's a step-by-step explanation of how to apply it. Addressing your description. Identify the chain rule form. Look for an integrand of the form f prime of g of x and g prime of x, or multiplied by g prime of x, where, g prime is the inner function, blah, blah, blah. Okay, example for this one. Okay, so we're going to choose u equals g of x, set u to the inner function g of x, compute du. Example, u of x. Okay. Replace f prime of g of x with f of u. Replace g prime of x dx with du. The integral becomes f prime of u times du. Okay, so find the antiderivative of f prime, which is fu, or f. Okay, so we're talking about standard antiderivatives here. No clue what they're talking about. Oh, I think we actually did learn about this in... Yeah, I'm pretty sure there are standard antiderivatives for the... we might have to memorize those as well. Okay, so... Antiderivatives for functions. Okay. Could you describe how we get the antiderivative if we don't use the power rule? I wasn't aware this was possible. Understanding the reverse chain rule and antiderivatives. The reverse chain rule is used to find the antiderivative. Yeah, okay. Identify the form. Without the power rule, let's walk through several examples of integration by substitution where the power rule doesn't apply. Oh, I reached my query limit. This right here. We substitute back. Okay. I think that's reasonable. Okay, so I understand. I think I understand everything now. I think the big thing, or one of the big things that I wasn't getting, was that you can take the antiderivatives of things that do not have, or without using the power rule. I thought the power rule was like the tried and true, like the thing for doing antiderivatives, and now I've identified that was incorrect. And I guess this right here is a good sort of lesson learned from the benefit of using a structured plan, or the benefit of using something like a textbook for structuring your learning, because in a textbook it's certainly not the case that I would have not become aware of something like finding an antiderivative without it would not have been the case that I could have found the antiderivative without, in a textbook it would be the case that I would have been exposed to the standard antiderivatives, right? But clearly that didn't occur, right? So yeah, maybe I need to update there that on the usefulness of a textbook, and perhaps where something like just using a large language model to identify everything would go amiss. Yeah. Maybe I'll have a little section, a little lessons learned. Okay, let's see. So if not using a textbook and only using a large language model, or just from referencing a test, it is entirely reasonable. Let's see. You are likely to, or I guess, you will often miss items that plainly exist within a textbook. That are not tested on the test, or don't happen to be mentioned by the large language model. In one way, in one way, in one regard, In one regard, the content wasn't on the test. And if your completion of the test is your learning goal, you still completed your learning goal. This suggests your test wasn't sufficient for learning, for testing everything you wanted to learn. To ensure that your goal includes everything you want to learn. Refine your goal by selecting a textbook or something similar, or something similar. Yeah. And generating your selecting a textbook or something similar. Or some Okay, I think that is an important lesson. If I spend more time on it, I think I could boil that down better. Right now it's a little verbose. But yeah. And then I also think when interacting with the domain, you should... Oh, actually, I don't know if you can see this. Okay, whoops. With a domain... when interacting with the domain, you should not overly focus, or let's see, you should have a correct level of focus. On the, procedural versus declarative. Procedural versus declarative knowledge. Yeah, I'd say knowledge. Correct level of focus. If you nail the knowledge, but don't invest sufficient time learning the procedural, you will probably still you will end up lacking. Of course, I spent too much time. Or well, I think I spent I valued the procedural too much, probably. Sorry, the declarative. Okay, and then the declarative is like conceptual stuff, whereas the procedural is like, okay, you know what the power rule is, like do the power rule. And I found that like I'm still honestly a little resistant to doing the procedural stuff. Maybe because I like the cognitive and like the ideas aspect of it more, but who knows? Who knows? Yeah. Let's see. Okay. Any other lessons learned that I can like note? I think another thing that was like really powerful is that when I started a new learning day, it was, let's see, when I started a new learning day, it was really powerful to have context for the previous days, for the previous day's work. It enabled me to kind of start up where I had left off. Oh my heavens me. Okay. What other things were beneficial? Okay, maybe like one of the lessons learned is that in identifying something I lacked, I think I could have clarified my goal more. I had a clear goal and interacted with, yeah, I think I could have clarified my goal from the start more. Well, no, I think my goal was like, it was clear in, clear in one regard, but it wasn't like it was clear, but I didn't exactly know everything. Yeah, okay, this is it. So it was clear, but I didn't know exactly what my goal entailed, right? The big thing that I'm finding right now is that there is an approach for taking an antiderivative or for taking an integral that doesn't involve using the power rule. And I thought the power rule was the thing used for all operations. And so there's that. Yeah, so I think I think, honestly, I think probably going through a textbook would have been like helpful, at least skimming through it, because let me grab one. Where is that? Okay. So let's pop open this textbook here. So I'm pretty much just going to go quickly to the sort of the index and identify what we have going on here. Okay, so yeah, so part 3 of the contents here is deals with derivatives and integrals. So I'm going to navigate to so I'm going to go to derivatives first to see if it's clear, like immediately, so I'm going to go derivatives and then differentiation. And following those, or sorry, integrals. Lols. Yeah, so I'm going to go to integrals first, and then 250. Okay, so okay, let's see. Okay, so I guess I'll describe what I'm seeing here. It's the case that maybe this is the way just math books are approached, but the entire chapter is mostly proofs and theorems, and doesn't, like, at least from my look of, just the pretty much entire chapter on integrals, doesn't describe how integrals are done. Like, there's no power rule here. Okay, maybe we'll go back to see if we have a, like, I forgot what they're called, but, oh, no, sorry. When I said index initially, I meant table of contents. We're actually going to the index now. And I'm going to look up to see if we have power rule, because that should bring us to a point that we have power rule. Power rule. Okay, yeah, I'm not seeing that in the index. That's super odd. I'm really surprised by that. I think I'm going to head to the other section because of the nature of like the interaction between integrals and derivatives. It may be that this would seem odd to me that the description for how to do integrals is in the differentiation section, or either that or the fundamental theorem of calculus section. So we'll try those two now. I should be getting back to the tech exam, but I think this is a good exploration. Because if I were to just have studied this book, then I would have had much like a much different experience, right? And so, you know, how does this compare to what would have occurred had I used the book? Oh, okay. So, yeah, it does say derivatives and integrals. Okay, so part 3. Oh, part 3 is derivatives and integrals. Oh, okay, I see. Never mind. So we're learning about the tangent line. Yeah, I'm really not. At least it's not abundant. Like it's not like abundantly clear. I'd have to read through the chapter, see if it identifies. There's nothing that like pops out with it. Anyway, so that was interesting. I'm sure if I read through the whole thing, then it'd be like more clear. Yeah. Okay. So I think. So we did the power rule section. I think I'd like to notate that I need to check for. Oh, and actually, I think we're at 2 hours now. So I need to check. Oh, actually, we might be able to just. Taking integrals when we can't use the power rule. Okay, so I think I'm going to stop there for today. I was assuming to get through more, but we did kind of go down a rabbit hole, which was like a beneficial one because the power rule and, sorry, the chain rule and the reverse chain rule are like, you know, pretty important. But yeah, like we didn't actually move past any of them, which was surprising. I thought I was going to get through pretty much the rest of this today. I feel like these next few ones are going to, well, I guess that's my feeling every time I interact with the exam. So, well, maybe I gotta adjust that. But yeah, I think this is good. I will end here, and then I'll catch you guys on. I think Monday will be the next stream. I'll see ya.